Okay, question 9. Does anyone have an answer for me for this one here? Victoria, what did you do for question 9? C? Alright, does everyone agree? Logan? Okay, you think E, so do you think C and E? Yeah, okay, C and E. Anyone else have anything else to add? What did you put down there, Ben?
A2.
A as well, so A, C, and E. Anyone else? What did you put down, Amber?
Technically, asked my sister what else there might be, but I put down all assumptions, I don't know what didn't indicate the direction that
Who'd you ask, sorry?
my sister.
Oh, your sister. Well, your sister's a smart cookie. The answer is all of them. The answer is all of them. Now, this question reads, which objects could be moving to the right? Now remember, if you have an unbalanced force, what does that tell you? Excellent, there we go. Acceleration, right? You have an acceleration. It does not tell you your direction of motion, it just tells you your acceleration. So for all of these objects here, I could describe a situation in which it is traveling to the right. I could, for all of them. This one here, is there any unbalanced forces? For A. What do you think? Are all the arrows equal and opposite? They are, right? So all of the arrows here are equal and opposite, therefore there is no net force, there is no acceleration. This could represent an object that is traveling with a constant velocity to the right. Right? If it has no acceleration, you could be traveling at a constant velocity to the right. Think of a car that's accelerated up to 100 kilometers an hour, and now the forces are the force of friction and the force of your engine, right? It's balanced out and you're maintaining that velocity. What about this object here? B. Okay, I want to take a stab at that. How could you describe that object moving to the right? Is there an unbalanced force? No. This could easily be my example of like a frictionless plane, right? If you give it a little tiny shove, it'll just move at that velocity forever. So again, there is no net force. That does not mean your object is not traveling at a constant velocity. It doesn't mean it's at rest. It could be traveling with a constant velocity to the right. How about C? Well, which way is it accelerating? It has an unbalanced force to the right, so it's accelerating to the right, right? So this is an object that could be speeding up in the rightward direction. What about this object here, D? Which way is its acceleration? Which way is that object accelerating? D. To the left. To the left. So this object could be the example I gave of like the textbook I was pushing across the table, right? As soon as that textbook leaves my finger, or as soon as this, say, whiteboard brush here leaves my finger, what starts happening to it? Starts to slow down due to friction. So this could be an object that is slowing down due to friction, right? It's traveling right and slowing down. Its acceleration is to the left. What about this object here? Which way is its acceleration?
To the left.
Yeah, it has a net force to the left. Again, this could be an object that's traveling right and slowing down. So this is a bit of a, I would say, trick question, but it really tests your understanding of force, acceleration, and motion. Remember, acceleration does not tell you the direction of motion. It simply just tells you how your velocity is changing, right? It's telling you the change in your state of motion. Alright, so yesterday we explored force. Today, we are going to be exploring Newton's second law. So today we are going to be exploring Newton's second law. Now his second law is technically this paragraph right here. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction of the net force, and inversely proportional to the mass of the object. More commonly, we write it like this. Acceleration is equal to the net force over mass, and often we rearrange this equation to be this. And this is how you are going to see Newton's second law from now on. Right? We just took this paragraph and we turned it into an equation. So our net force is equal to mass times acceleration. Okay? Where is it? There it is. So for example, let's say I accelerated a 2 kilogram object with an acceleration of, 2 meters per second squared, right? So I'm putting a force on an object, a 2 kilogram object, that is causing it to accelerate at 2 meters per second squared. What would be my force in that situation? So 2 kilograms, 2 meters per second squared. What would be my force? Yeah, it'd be 4. Now, it'd be 4. So, looking at this equation, we can do some proportionality problems. So we can make some assessments based on how we're changing mass or changing acceleration or changing force. So for example, if I, say, doubled my mass and I wanted to maintain the same acceleration, how much more force would I have to exert? Ooh, okay, we're going to go through quite a few practice problems then on this. So first let's explore the relationships here. So force is proportional to mass. If things are proportional, that means if we increase one, we increase the other by the same fractional amount. So if I double my mass, I am going to need double the force in order to cause the same acceleration. If I half the mass, I need half the force to cause the same acceleration. Force is also proportional to acceleration. So the greater the force I apply, the more my object is going to accelerate. So let's say I had a 2 kilogram object again, and I doubled the force on that object, the force that object was experiencing, I would double the acceleration. If I half the force, I half the acceleration. And then lastly, we have mass. Mass is inversely proportional to acceleration. So given the same force, the heavier the object, the less that object will accelerate. And you already have somewhat of an intuitive idea of this concept. Because inertia is what? How do we describe inertia? How do we describe inertia? It's resistance to... Yeah, it's resistance to changes in its state of motion, changes in its velocity, and therefore it's resistance to acceleration, right? So the more mass of the object, because remember, inertia is dependent upon mass, the more mass of the object, the more it resists acceleration, right? It's why pushing a train, right, a locomotive on a train, you got to exert a lot of force in order to even mildly accelerate that extremely heavy train. Whereas something as simple as my eraser here, it doesn't take much force to get it to accelerate. Alright, so if I doubled the mass of my object, I will half the acceleration. And if I say, let's say half the mass, I will double the acceleration of my object, given the same force, of course. So let's do a couple practice problems briefly that explore this proportionality. So let's say I had an object. We're not going to use real numbers here. Let's just use fake numbers. So let's say that given some force, we don't know what the force is. Right, we have force is equal to mass times acceleration. Let's say on our object, let's say I double the mass. And let's say I triple the acceleration. Let's say I double the mass and I triple the acceleration. What impact is that going to have on my force? What is going to happen to my force? Is mass and force directly proportional? If I increase one, will the other increase by the same fractional amount? Yeah, it will, right? It will. They are directly proportional. Is acceleration and force directly proportional? They are, right? They are. So you can think about this intuitively, right? If I doubled the mass, is it going to require more force to push the object at the same acceleration?
Yes.
Of course it will, right? If I wanted to achieve an acceleration that's 3 times as great, am I going to have to push a lot harder?
Yes.
Right, I am. So the answer is to achieve the this here, right? I want to triple the acceleration with double the mass. How much more force am I going to have to exert? 2 times as much, 3 times as much, 5 times as much, 6 times, 7 times, 8 times. I heard it. Yeah, you're going to have to push 6 times as hard, right? You're going to need 6 times the force. Does that make sense to everyone? I've seen some perplexed looks. Well, think of it this way. Let's plug in some fake numbers, and that usually will ease the anxiety. So the force needs to be, is 6 times higher in this situation, right? We need 6 times the force. Now, if we plug in fake numbers, you will clearly see right away what I mean. So let's say we had a force of, originally, of 1 Newton, and we had a mass of 1 kilogram, and we had an acceleration of 1 meter per second squared. So let's keep things really simple. Now, if I double the mass, what is my new mass? That's right, it's 2 kilograms. If I triple the acceleration, what is my new acceleration?
3 meters a second.
3 meters per second squared. And therefore, what is my new force? What's 2 times 3? 6. We're going to break down that unit in a little bit here, the Newton. But it'd be 6. So our force is 6 times higher. Now this is a pretty good strategy to utilize in all science. If you're ever curious about a relationship, you can always plug in fake numbers and just do the math. Okay? So it is 6 times higher. let's look at a different example. Let's say we had a situation instead where, yes? Yeah, of course. Let's say we had a situation where we, let's say we triple the mass. Okay, we triple the mass, and we quadruple the force. What will be my object's acceleration? Here I'm talking relatively. What will my acceleration change by? So if I rearrange this equation to make it equal to acceleration, we'll have acceleration is equal to force over mass. What impact does mass have on my acceleration? Are they directly proportional or inversely proportional? They're inversely proportional, right? As one goes down, the other goes up. So if I triple my mass, what impact does that have on my acceleration? Is that going to make my object accelerate faster under the same force or slower? Right, we're going to have less acceleration. Makes sense. If I increase the weight of that object, that same push is going to cause less acceleration. So that's going to decrease my acceleration. If I quadruple the force, quadruple the shove I'm giving that object, is that going to make my acceleration go up or down?
Up.
Right, they are directly proportional. It's going to increase. So what impact will this have on my acceleration? How much does my acceleration increase or decrease by? If we triple our mass and we quadruple our force, what impact will that have on our acceleration? In essence, what we're doing is dividing by 3 and timesing by 4. Right? Acceleration and mass are inversely proportional, so we are going to divide by 3. It's 3 times less. And then we quadruple the force, we're multiplying by 4. Kara, do you have a question? Are you sure?
Yeah.
Okay. Alright, so I could say that my acceleration is going to be 4/3 greater. Does that make sense? Yes?
Do we always put it in fractions, not decimals?
I mean, you can do either. I like fractions though because is this going to be a number that just continues on forever? Yeah, it's 1.33333333 forever, right? So a fraction is a nice way to represent that without having to do 1.333 continuing. So let's do another example. Let's say I don't know, let's say I halved my mass and I tripled my force. Half my mass and I tripled my force. What impact would that have on the acceleration of your object? What impact would that have on your acceleration? Well, what impact would halving my mass have on my acceleration? How much bigger or smaller would my acceleration be? Half bigger? Are they directly proportional or inversely proportional? Mass and acceleration. inversely, right? If I decrease my mass, I increase my acceleration. So if I halve my mass, how much bigger is my acceleration? Thank you, Alana. It's double, right? It's double. So I've doubled my acceleration as a result of this. And what happens here to my acceleration due to force? If I triple my force, what happens to my acceleration? They are directly proportional. You triple your acceleration. So what effect, net effect, does that have on my acceleration? Right here, we are going to double it, and here we are going to triple it. So what is my new acceleration? How many times bigger is it?
6 times.
Yeah, my acceleration is 6 times greater. Right, again, if that's confusing to you, you can just plug in fake numbers. We can say originally our acceleration was, I don't know, 1 meter per second squared. Our force was 1 Newton, and our mass was 1 kilogram. Now, if I half my mass, well, that's 0.5 kilograms. If I triple my force, that's 3 newtons. Well, what's 3 divided by 0.5? It's 6. Divided by 0.5 is the same as multiplying by 2, right? So that would be 6 meters per second squared. So again, if you're ever confused, you can just plug in fake numbers, okay? Any questions? No? So being able to analyze without having numbers present, it's actually a pretty important skill. One that is very commonly tested in science. In fact, if you want to get into med school and you write the MCAT, the test you need to get in, a lot of the questions they give you are just going to be this like super crazy big equation in the physical sciences section. And they'll say, okay, well, if I change this by this, what happens, right? So you're going to have to really be able to work with variables if you want to succeed, for example, on the MCAT. All right, so how is force measured? I've talked about it a little bit here. It's measured in newtons. Now, a newton is a kilogram times meter per second squared. So whenever we are dealing with Newton's second law, you may want to write this down. Our mass is always going to be given in what? Yeah, excellent. So if I give you your mass in something else, if I say I give you grams, or I give you pounds, or I give you any other unit of mass, what do you have to convert it to?
Kilograms.
Kilograms, always. Okay? So that's super important. You may want to asterisk that. It has to always be kilograms. Your units of acceleration, what do they always have to be? Meters per second squared. Okay, so the reason for this is because the technical definition of a Newton is the amount of force required to accelerate a 1 kilogram object to 1 meter per second squared. Or sorry, to cause an acceleration of 1 meter per second squared in a 1 kilogram object. So very important that you convert to kilograms if your units are not kilograms, and you convert to meters per second squared if your units are not meters per second squared. I'm probably not going to be that mean though. I'm not going to give you a ton of conversions to do. But I will give you a couple, so you got to watch out for that. Alright, now most of your life, you will have used the words weight and mass incorrectly, right? Because when you want to know how much an individual's mass is, what do you ask them? Please don't ask people this, but what do you normally ask them?
How much do you weigh?
Yeah, how much do you weigh, right? But your weight is actually a unit of force. Mass is what we measure in kilograms or grams, okay? Mass is an intrinsic property of all matter in the universe, irrespective of where it is. So, you know, my mass is, oh God, I do some quick math here. It's something like 70 kilograms, approximately, probably a little less than that. Something like 70 kilograms, and that is the same on Earth, that is the same in outer space, that is the same on the moon. Now, my weight, however, is my force due to gravity. So my weight is going to be the force I am pushing on the ground with right now. Is that constant everywhere in the universe? No. When you're in outer space and you're floating around, you are what? You are lighter. There's a word for it. You're floating around, you are weightless. You are weightless, right? You have no weight because there is no force due to gravity exerted on your body. Now, what about if you're on the moon? Is my weight the same? No, right? There's way less gravity on the moon, so you have much less weight on the moon. Right? If you stepped on a scale on the moon, the number would be way less than a scale on Earth, right? Because you were exerting less weight on the ground. So, how then do we figure out somebody's weight? Well, like I said, I have a mass of approximately 70 kilograms. Probably 65 is a better number. We'll say 65. Now, the acceleration due to gravity on our planet, it does fluctuate depending on the density of Earth below you, but not by a whole bunch. Less than a tenth, pretty much. It fluctuates by like, 0.1 here or there, depending where you are. But there's actually a plate somewhere in Winnipeg, I forgot where it is, that actually says like at this point, acceleration due to gravity is 9.8 meters per second squared. So in this course, we're going to treat g as a constant. Everywhere on Earth, your acceleration due to gravity is constant. It is 9.8 meters per second squared. Now, how then do we figure out somebody's weight, their force due to gravity? We're going to use Mr. Salt as an example. So my force due to gravity, Fg is what we're going to write it as, is going to be mass times acceleration, and my acceleration here is 9.8 meters per second squared. I'm feeling a little lazy though, I'm just going to round that up to 10. What did I say my mass was? 65 kilograms. And like I said, I'm going to be a little lazy here. I'm going to round this up to 10 meters per second squared. Now, as a result, what is my weight? What is my weight? Hmm? 65 times 10 is 6.5. What is 65 times 10? Yeah, 650. And what are the units of force? What are the units of force? It's newtons, right? Newtons. So my weight is 650 newtons. My mass is 65 kilograms. Now, this difference between weight and mass is extremely important. We're going to be using this quite a bit to solve for Newton's second law problems. Okay? So your weight is a unit of force. Your mass is the same everywhere in the universe. The next type of force I want to talk a little bit more about is friction. If an object is moving, it is experiencing friction on our planet. There's really no such thing here as a frictionless plane. And importantly, friction always opposes your direction of movement. Always. So if I jump out of a plane and I start falling towards the Earth, well, I'm going to be hitting air molecules, and the more air molecules I hit and the faster I hit them, the more air resistance there is. So if I'm falling down to the earth, which way is air resistance? It always opposes motion. Yeah, it's up, right? If I push this controller, if I push it to the right here, which way is friction? It's to the left. It always opposes your direction of motion. So let's draw a couple diagrams, and then we're going to, I'm going to let you work quite a bit in your workbooks today. But first let's analyze a couple free body diagrams. So if I was to draw a free body diagram for these two examples right here. So an object being pushed on a table to the right with a force of 20 newtons experiences a frictional force of 10 newtons. So with a free body diagram, we're going to draw a box. Everything gets reduced down to a square. And what else am I going to draw? Am I going to draw an arrow like this and like this for our force applied, right, 20 newtons, and our force of friction, 10 newtons? Would that be right? Why not? Why would that be wrong? Yeah, Kiara?
Because the force of friction is going against the force.
It always goes against your direction of motion, right? So if we are moving in this direction, accelerating in this direction, our force of friction is going to be in this direction here. It always opposes your direction of motion. Right, it always opposes your direction of motion. Now, the second example, we have a free-falling object with a weight of 50 newtons. It experiences an air resistance of 20 newtons. So which way am I going to draw the arrows on this one? You're right in one direction, yes? So weight is always which direction?
Down.
Yeah, like the center of the earth. Down, right? So it's going to be down. So my force due to gravity, aka my weight, is going to be 50 newtons. And my force of air resistance, which direction am I going to put that in? Good job. And that's going to be my force of, say, air resistance, and that is going to be 20 newtons. Skill testing question for you. What is the mass of this object? We're going to assume we're on Earth here, by the way. We're going to assume we're on Earth. What is the mass of this object here on Earth? Skill testing question. What is Newton's second law? What's the formula? What is the formula? It's not a trick question. What's the formula? Net force is equal to mass times acceleration. So here, our force due to gravity must be equal to mass times acceleration. And what is acceleration due to gravity on Earth? Yeah, 9.8 meters per second squared. I'm going to be lazy. That's what we call G, by the way. I'm going to be lazy and just round it up to 10. Now, we have our force. We know what our acceleration is. How do I solve for m? How do I solve for m, our mass? Yeah, you're right. So our mass is going to be equal to our weight divided by our acceleration due to gravity. That is 50 newtons divided by 10 meters per second squared. So what is the mass of this object? What is the mass of this object? Thank you. It's 5 what? What's the unit? Kilograms. Well done. So that's 5 kilograms. So given the weight of your object, you can determine its mass. It's kind of another important idea. So given the weight of your object, you can determine its mass.
Mr. Sol,
Yes?
does it not cancel, or not cancel each other out, but 50 take away 20?
Excellent. So if we wanted to figure out how fast our object was accelerating, we could do that now. So now that we know the mass of our object, we could figure out its acceleration. What is the acceleration based off of? You guys did this worksheet last class yesterday. What is your acceleration based off of? So if you have an unbalanced force, is there an acceleration?
Yes.
Thank you. Yes, you're all nodding yes, right? Yes. What is our unbalanced force here, our net force? What is our sum of all forces? You're right, it is what?
30.
Yeah, it's 30 newtons. In which direction?
Down.
Down. I wasn't necessarily planning on doing this right now, but why not? So 30 newtons down. So how can I figure out how fast it's accelerating? We're going to use that same formula. How can I figure out how fast it is accelerating? Well, what would acceleration be equal to? Yeah, it's going to be your force divided by your mass, right? If I rearrange F is equal to ma, well, my acceleration is going to be equal to my force divided by my mass. And when we are finding our acceleration, it is always the unbalanced force. It's always your net force that you will be utilizing. So this is going to be 30 divided by 5, which is what? 6 meters per second squared. So this object is falling down towards the Earth currently with an acceleration of 6 meters per second squared. So with a couple force factors, we can figure out a lot of information about our object. We can determine its acceleration, which is based on the net force, and we can figure out its mass. In fact, you have to figure out its mass to figure out the acceleration. All right, let's look at another example here. So a free-falling object weighing 80 kilograms experiences an air resistance of 600 newtons. What is the net force on the object, and how fast does it accelerate? So based on what I just showed you, take a minute right now. I want to see if you can try to do this on your own. So try to figure out the net force and the resultant acceleration. Let's go over this question. Most of you here made the same mistake. Are mass and weight the same thing? They aren't, right? They aren't. So I gave you look, even I made the mistake in my wording here. Weighing 80 kilograms. What should I have said? Yeah, I should have said an object with a mass of 80 kilograms. Let's change that right now, actually, so I don't forget. Even I make that mistake because we use weight in terms of mass all the time. So a free-falling object with a mass of 80 kilograms experiences an air resistance of 600 newtons. What is the net force on the object? Now, whenever you are given a problem like this in physics, in fact, pretty much any physics problem, the first thing you should do is draw a diagram. So super important, let's draw a diagram first. So our free body diagram, we have an air resistance of 600 newtons. Which direction will that air resistance be?
Up.
Good job. Right, we're falling towards the Earth, therefore our air resistance is going to be up, and that's gonna be 600 newtons. Now, when I walked around, the mistake I saw was this. A lot of you did this. You wrote 80 kilograms as my downward force. But is 80 kilograms a force? What is that? That's your mass. We need to know the force due to gravity pulling this object down. So, what is my force due to gravity? Well, it's going to be my mass times g. What is our mass? 80 kilograms. What is g? 9.8 meters per second squared. Again, I'm going to be kind of lazy here. I'm just going to do 10 because mental math. So what is my downward force? 800 newtons. Excellent. So that is my downward force. Not 80, but 800 newtons. So in which direction is my net force? My sum of all forces. Once we cancel things out, which direction is it?
Down.
It's down. How much left over do we have if we look?
200 newtons.
We have 200. So my net force here is 200 newtons down. 200 newtons down. Now, how then can I figure out my acceleration? What is my acceleration equal to? Rearrange that formula. Newton's second law is F is equal to ma. What is A equal to? Yes, my acceleration is my force divided by my mass. And here, when we are finding acceleration, we must use net force. Okay, we must use our net force. And that's going to be 200 newtons divided by 80 kilograms. Which is 2.5 meters per second squared. 2.5 meters per second squared. I would mark that wrong though. I'd want to take half a mark off. What am I missing? Yeah, you're right. You said that? Down, right? We're missing the direction. Down. Because acceleration is a vector just like force. Okay?